Proxima Centauri, the nearest star to our planetary system, has for some time been a subject of interest for space experts. This little red person was found in 1915 by Scottish space ace Robert Innes. It is principal to the Alpha Centauri framework, which also incorporates Alpha Centauri A and B. In spite of its nearness, simply 4.24 light-years away, Proxima Centauri remains intangible to the naked eye because of its low brilliance. Anyway, Proxima Centauri holds gigantic scientific importance, particularly as the host star of Proxima B, an exoplanet that orbits within the star's habitable zone. Red dwarfs like Proxima Centauri and its cousin Tutty are more unassuming, cooler, and far longer-lived than stars like our Sun. Their low luminosity makes them hard to notice, yet it also suggests that their habitable zones are much closer to the star. For Proxima Centauri, this implies an orbital distance of roughly 0.05 astronomical units, just a little part of the distance between Earth and the Sun. This closeness opens Proxima B to significant stellar activity, including ordinary solar flares and elevated levels of radiation, making its environment vastly different from Earth's. The discovery of Proxima B was an immense forward leap in exoplanet research. Utilizing the radial velocity method, space specialists identified subtle wobbles in Proxima Centauri's position, caused by the gravitational pull of an orbiting planet. These wobbles allowed researchers to estimate the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the presence of Proxima B, marking a significant step forward in the search for potentially habitable worlds beyond our nearby planetary system. While ground-based observations have provided valuable insights into Proxima B, they come with major limitations, such as atmospheric distortion and light pollution, which hinder the ability of Earth-based telescopes to capture detailed data about the planet's surface or atmosphere. Much of the data we have, including its mass, distance from the star, and orbital attributes, comes from indirect measurements. To uncover further insights into Proxima B's environment and its potential for life, advanced observational instruments like the James Webb Space Telescope, JWST, are essential. Proxima Centauri and Tutty's role as a gateway to understanding exoplanetary systems couldn't be more significant. As the nearest star system to Earth, it offers a unique opportunity to study the conditions necessary for life. Proxima B, in particular, presents a tempting prospect. A roughly Earth-sized planet with the potential to harbor water and perhaps even life. However, the challenges posed by its harsh environment make it a complex puzzle for scientists. The James Webb Space Telescope isn't just another tool in the arsenal of space science. It is a revolutionary instrument designed as the successor to the Hubble Space Telescope. JWST was built to overcome the limitations of its predecessor and push the boundaries of human knowledge. While Hubble has provided critical insights into the universe, including the age of the cosmos and the discovery of countless galaxies, its capabilities are limited by its focus on visible and ultraviolet light. JWST, on the other hand, is designed to observe the universe in infrared frequencies, allowing it to peer through vast amounts of dust and reveal features hidden from Hubble. One of JWST's key design features is its primary mirror, which spans an impressive 6.5 meters in diameter, more than twice the size of Hubble's mirror. This larger mirror enables JWST to gather much more light, making it capable of observing even the faintest and most distant objects. The mirror is coated with a thin layer of gold to enhance its infrared reflectivity, and is composed of 18 hexagonal segments that work together to form an extraordinarily sensitive observational platform. Another remarkable advancement is JWST's sunshield, which keeps the telescope's instruments at a steady temperature of about -233 degrees Celsius. This ultra-cold environment is crucial for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point, L2, a stable position about 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to maintain continuous observations. JWST can focus on everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its ability to detect infrared light is particularly important, as it allows researchers to study redshifted objects, those whose light has been stretched to longer wavelengths as the universe expands. JWST's capabilities extend far beyond simple observation. It is designed to answer some of the most fundamental questions in science, including the origins of galaxies, the formation of stars, and the conditions that could support life on other planets. With its advanced instruments such as the Near-Infrared Camera, NIR-CAM, the Mid-Infrared Instrument, MIRI, and the Near-Infrared Spectrograph, NIR-SPEC, JWST isn't just a telescope. It's a time machine, a laboratory, and a testament to human ingenuity. Proxima B has captivated both scientists and the general public as a potential second Earth, positioned within its star's habitable zone. The planet has the right conditions to support liquid water, a fundamental requirement for life as we know it. With a mass roughly 1.17 times that of Earth, Proxima B is likely a rocky planet, similar in composition to our own. Its proximity to Earth, just over 4 light-years away, makes it an ideal target for studying the potential for life beyond our solar system. However, Proxima B is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual daylight while the other is in perpetual darkness. This creates a unique climate with extreme temperature differences between the two hemispheres. The region where day meets night, known as the Terminator line, could offer a narrow habitable zone with conditions mild enough to support life. The challenges posed by Proxima B's environment are significant. Its host star, Proxima Centauri, is a red dwarf known for its intense solar flares, which can release bursts of X-rays and ultraviolet radiation. These flares could strip away the planet's atmosphere over time, exposing its surface to the harshness of space. If Proxima B retains any atmosphere, it would require a strong magnetic field to protect it from radiation. Without such protection, its surface environment would be hostile to life as we know it. Despite these challenges, scientists remain hopeful about the potential for life on Proxima B. The planet's location in the habitable zone suggests that liquid water could exist, either on its surface or in subsurface reserves. Life might adapt to the harsh conditions, just as Earth organisms thrive in extreme environments like deep-sea hydrothermal vents or high radiation zones. These adaptations could include radiation resistance, subsurface habitats, or novel biochemical processes. The search for life on Proxima B is more than just a scientific endeavor. It is a quest to answer one of humanity's oldest questions. Are we alone in the universe? Proxima B represents an exciting opportunity, a rocky, Earth-like world that could harbor the conditions necessary for life. As our technology advances, so too does our ability to explore this intriguing planet and uncover its secrets. While Proxima B presents tantalizing possibilities, its climate is heavily influenced by the nature of its host star, Proxima Centauri. Unlike our Sun, Proxima Centauri is a red dwarf, smaller, cooler, and much less luminous. Its reduced size and temperature mean that its habitable zone is much closer, placing Proxima B in an orbit just 0.05 astronomical units from the star, about 20 times closer than Earth is to the Sun. This nearness makes a special arrangement of challenges for the planet and any potential life it could hold. One huge issue is Proxima Centauri's heavenly action, especially its serious and incessant sun-powered flares. These flares are abrupt, strong explosions of energy that discharge high portions of X-rays and ultraviolet radiation. Such occasions are undeniably more normal and extraordinary in red dwarfs than in stars like our Sun. For Proxima B, this implies a steady inundation of high-energy particles that could strip away the planet's climate over time. Without a defensive attractive field like Earth's magnetosphere, any environment on Proxima B would be defenseless against disintegration, leaving its surface exposed to cruel radiation. Even if Proxima B holds a portion of its environment, the radiation from Proxima Centauri presents critical difficulties to life. Elevated degrees of ultraviolet radiation can break synthetic bonds, preventing the formation of complex organic molecules. This would harshly limit the potential for life to develop or, on the other hand, sustain itself on the world's surface. On Earth, creatures like Deinococcus radiodurans have developed systems to fix DNA damage brought about by radiation, suggesting that life on Proxima B may also adapt. However, the degree of radiation resistance required would be extreme, potentially requiring entirely new biochemistries. Intriguingly, Proxima B's tidally locked nature could offer some protection. While one side of the planet faces steady radiation from Proxima Centauri, the dark side could act as a shelter. Subsurface habitats or deep caverns could protect potential living things from the most extreme radiation. Moreover, if Proxima B has subsurface seas, they could provide a stable radiation-free environment where microbial life could flourish, similar to the ecosystems around hydrothermal vents on Earth. Notwithstanding these challenges, researchers remain hopeful that Proxima B's extreme climate offers an interesting opportunity to study the resilience of life. By examining how life forms could survive or, indeed, even flourish under such circumstances, scientists can expand their understanding of what makes a planet habitable. Proxima B isn't simply a potential home for life. It is a laboratory in the quest for life's resilience across the universe. The plausibility of life on Proxima B raises more questions than it answers, but it also offers another perspective on the meaning of livability. The search for life on Proxima B isn't just a scientific mission, but also a philosophical one. It challenges our understanding of what constitutes a livable climate and broadens our search for life to include planets with extreme conditions. Proxima B's hostile radiation environment and tidal locking force scientists to reconsider the traditional idea of livability, which was largely based on Earth-like conditions. One of the key aspects of studying Proxima B is its potential to reveal new insights into how life could adapt to harsh conditions. If life could indeed survive and thrive in such an extreme climate, it could redefine our assumptions about where life may exist in the universe. Grasping these possibilities might help researchers focus on other exoplanets that share similar characteristics to Proxima B, expanding the criteria used to identify potentially habitable worlds. The study of Proxima B also fits into the broader context of the search for exoplanets, planets that exist outside our solar system. In the past few decades, the discovery of exoplanets has exploded, with thousands of these distant worlds now identified. The study of these planets, especially those in their stars' habitable zones, has shifted our perspective on the likelihood of finding life elsewhere. Proxima B, with its proximity and potential for liquid water, is one of the most intriguing candidates. However, it is far from unique. As technology advances, the number of known potentially habitable exoplanets continues to grow. As well as studying Proxima B, space experts are focusing on planets around other stars, especially those that share characteristics with our Sun. These Sun-like stars offer habitable zones that might be more stable and conducive to life. However, Proxima B, orbiting a red dwarf star, presents a contrasting case that challenges traditional thinking about livability. Its study can provide valuable lessons on the resilience of life and how it might exist under more extreme conditions. Proxima Centauri, the star that hosts Proxima B, also offers scientists a fascinating opportunity to better understand stellar behavior, especially the differences between stars like our Sun and red dwarfs. Red dwarfs are far more common in the universe than Sun-like stars, and studying these stars can help us understand how different types of stars influence the potential for life on surrounding planets. Proxima Centauri's frequent stellar flares, as well as the effects of its intense radiation on Proxima B's atmosphere, might help researchers understand how various types of stellar activity influence planetary conditions, providing essential insights for the search for life elsewhere. For now, Proxima B remains a mystery, but technological advances and future space missions may ultimately provide the data needed to answer one of humanity's most significant questions. Is there life beyond Earth? With each new discovery, the possibility of finding life on Proxima B or other exoplanets becomes more conceivable, and the implications of such a finding would be profound. The search for life beyond Earth continues to grow, and Proxima B remains a beacon for future exploration. The potential for finding extraterrestrial life on this exoplanet has sparked interest not only among astronomers and space researchers but also among the general public. Its location in the habitable zone of Proxima Centauri, combined with its Earth-like size and composition, makes it a captivating candidate for further study. However, the harsh environmental conditions present significant obstacles, prompting researchers to rethink the traditional boundaries of livability. One crucial aspect of Proxima B's study involves understanding how life could adapt to extreme conditions, such as intense radiation and temperature fluctuations. If microbial life or even more complex organisms exist or could survive there, they may have unique biological adaptations that allow them to endure these hostile conditions. Research into extremophiles, organisms on Earth that thrive in extreme environments, such as those living near hydrothermal vents or in acidic lakes, could offer valuable insights. These organisms rely on unusual biochemistry to survive, and similar adaptations may be found on Proxima B, suggesting that life elsewhere in the universe may not need to resemble life on Earth to thrive. Another avenue of investigation includes studying the planet's potential magnetic field. A strong magnetic field is crucial for shielding any atmosphere from being stripped away by solar winds and cosmic radiation. If Proxima B has such a magnetic shield, it would significantly improve its chances of maintaining a stable atmosphere suitable for supporting life. Recent advances in space-based instruments that can detect faint magnetic fields may help researchers better understand the composition and dynamics of Proxima B's atmosphere, providing further clues about its potential habitability. Looking beyond Proxima B, the study of red dwarfs and their planets opens up broader implications for understanding planetary systems. Red dwarfs are the most common type of star in the Milky Way, and many potentially habitable exoplanets orbit these stars. By understanding the relationship between red dwarfs and their planets, astronomers may be able to refine their methods for identifying habitable planets around other stars, increasing the likelihood of finding life elsewhere in the universe. The quest to understand Proxima B and its environment is not just about one planet, but rather about the broader context of life in the universe.